Okay, so we got antennas. We need to connect them to the radio. We call those feed lines, and there will be some connectors involved. Typically, you're going to use coaxial cable. In some cases, you may have ladder line or twin lead or open wire, which are, there's some pictures of window line and twin lead down at the bottom along with the coax. The reason that coax is most common is because it's easier to use. It isn't affected by other signals outside. It doesn't radiate signals, and it doesn't receive signals because of the coaxial effect, because the electric field is concentrated between the center conductor and the outer shield. In the case of the two-wire, what they call them open wire, the differences there are basically how far apart the two wires are, which changes the impedance. So if you're familiar with the old TV antenna, twin lead, it was 300 ohms. It's like a ½ inch or so separation. The ladder line comes in 450 and 600 ohm. They're separated farther apart. And then there's open wire, where it's two wires and you use some kind of plastic spacers, and I've seen them maybe 6 inches apart. The reason they use those is it's a balanced line. They're very low loss, less loss than you get in a coax. In a coax, you've got about between 25 and 30 picofarads per foot of capacitance, which is why you'll see in a later chart that the loss goes up significantly as you increase the frequency on the coax. You don't have that much of a problem with the twin lead, but at some point you do have to convert it back to 50 ohms impedance for your radio, because almost all transceivers will be 50 ohms. It says there's no special tools required for coax.
Certain crimper would be handy if you got a
you don't have to use a crimper. You can solder, and I guess solder is not a special tool per se. Most people will use a crimping tool and use crimp connectors.
So, just curious, fiber optics.
Yeah.
Are they used at all in any of this type of application?
Not that I'm aware of.
Yeah.
Maybe when you get up into the really high frequency stuff, when you're getting close to the speed of, the wavelength of light. Okay, so the most important parameter of the feed line is it's going to be its impedance. Now, they typically try to get an antenna to be around 50 ohms by using a balun or an unun as an impedance transformer to convert it to get it close to 50 ohms, because that's how you get your maximum current transfer. If the source impedance and the load impedance are the same, and the transmission line between them is same characteristic impedance, then basically you're going to get half of your power, which is the most you can get. Because it's 50 ohms to 50 ohms, you've lost half of it getting there. So you're either half your power actually getting there or less. And the impedance, which did we talk about impedance? Really?
I remember it, but maybe I read it too.
I don't think we talked much about impedance, but Impedance is the opposition to AC current flow, where resistance is the opposition to current flow. It doesn't care whether it's DC or light. Impedance is the frequency dependent part of the opposition to current flow. So if there's inductance or capacitance in the circuit, that will give you inductive or capacitive reactance, which is a parameter of impedance. Impedance is the vector sum of the capacitive and inductive reactances, and they cancel one another. One's positive, one's negative. So when you're resonant, it means that the inductive and capacitive reactances are equal and opposite. So all you have is resistance. So the impedance will equal the resistance at the resonant point. So you want the feed line impedance to match the transmitter and the antenna to get your maximum power transfer. So why is coax the most common feed line for amateur radio antenna systems? Yep. No, alpha.
Alpha. Okay.
That's large.
Yeah, I would go with alpha.
Yeah. Coax has more loss than the open wire or hard line, which we hadn't talked about, which is a special coax. It can't necessarily handle more power than an open wire line. And it's not necessarily less expensive. I mean, open wire line's fairly cheap. And some of your coax, your better coax, like LMR 400, is $200 to $250 a foot. Okay, what is impedance?
Mm.
Hey,
Did I turn alpha?
yeah.
It's not the inverse of resistance, which would be conductance, which is represented in Siemens, used to be Mohs. It's not the Q or the quality factor, which is sort of the ratio of the reactance to the resistive part of the inductant or capacitor. And it's not the power handling capability. So what is the unit of impedance?
Ohm.
All right.
You got a handheld, that would be like mobile home.
The old ohm. Okay. All right. Most amateur radio transmitters use a 50 ohm output impedance. Like I said, most antennas, they try to get them close to 50 ohms. And most of your coaxial cable that we're going to use is a 50 ohm or 52 ohm impedance. I think RG58 is sometimes 52 ohms. The TV cable that you're going to use, RG6, RG59, are 75 ohms. Now, sometimes that's used. Go ahead, Roger.
Now we're just getting a pretty good thunderstorm over here, so I'm hoping I'm staying online for you.
Okay. Yeah, it's raining here too.
And we're getting thunder and lightning over here.
Yeah, I hear some rumbling. The TV stuff, 75 ohms, sometimes is used to make a quarter wave matching transformer to go between 50 ohms and say 100 ohms. By putting a quarter wave length of 75 ohm coax in the middle, it acts as a transformer for that particular frequency. Now, most of the exam stuff deals with RG58, which is like about a quarter-inch diameter coax that's 50 ohms. You normally would use that inside the shack to make connections between your equipment because it's flexible. You're using short lengths because it's got higher loss than RG213. 213 is one of the half-inch coaxes that's also 50 ohms. It's much lower loss than RG58.
So do they make that stuff direct burial or open, or do you need to protect it if you're connecting outside?
Yes. There's direct burial versions. I think we might have lost some people. Who's still there?
I'm still on it. I'm still on it. Looks like Roger dropped.
Yeah. There's direct burial versions. There's some that are UV resistant, which you really need to get if it's going to be outside all the time.
Yeah.
And there's, I didn't bring my display board in, but I mean, there's probably a dozen different flavors of 50 ohm coax.
Yeah.
Here's a chart showing some of the more common ones. The main two to look at as far as exam questions are going to be RG58 and RG213. And the main thing is if you see as the frequency goes up, the loss will go from less than a dB up to almost 25 dB for RG58. And 213, you're looking at a third of a dB up to 12 dB. So it's half basically of the loss or less of the RG58.
And if you want to spend a lot of money, you can get the LMR 400.
LMR 400 on the chart. I mean, there's LMR 600, which is on there, which is bigger cable and less loss than that. And then there's hardline, which is basically copper tubing with the center conductor usually separate. It's an air dielectric, and they'll have a little kind of a spiral plastic thing that keeps the center conductor in the middle. That's extremely low loss. It's very expensive. It does take special tools in order to put connectors on and to keep it waterproof because it's got to be sealed.
Yeah.
So you almost have to weld it. I've got some pieces. I've never tried to do anything with it. It's very stiff. It's hard to bend. But they typically use that for repeater antennas because you're looking at operating at 2 meters or 70 centimeters. So you're up here in the 140, 440 range.
But they usually don't have to go too far with that.
Right. Usually they try to put the repeater up close to the antenna. So you're talking 25, 50 feet or so. Of course, now in the broadcast industry, I mean, they're running it all the way up the tower, but they got a lot of money and they're probably using, I think there's hardline that's like 4 inches in diameter. No telling what that costs, but in the broadcast industry, there's a lot of money involved. So they can afford it. They can afford all these radials to make the ground thing. So I guess we're not going to get Roger back.
Okay.
The main thing on this chart is to notice the difference in loss between the two and how much they change as they go up in frequency.
Roughly double.
Yeah. So what's the most common impedance of coaxial cables used in amateur radio?
Bravo.
600 would be one of the twin lead. Open wire, I think, is 600. What happens is the frequency of a signal in a coaxial cable is increased.
I would say D.
He's saying loss. Down. Did he say D?
He said D, delta.
Say frequency goes up, yeah, your loss will increase.
Which is why you wouldn't use RG58 for a 100-foot run at 2 meters. What's the electrical difference between RG58 and RG213 coaxial cable?
D.
Say that again,
Charlie,
Charlie.
Charlie? Okay. That's what I would put. Same given frequency, it's like half the loss. In practice, using RG58 at 80 meters is probably okay. If you remember the chart, it wasn't much loss down at that frequency, which would be, what's 80, 3.5 megahertz. But you certainly wouldn't and couldn't use it at 440. The loss, I mean, well, I guess you could, but you wouldn't get much of a signal to your antenna. Yeah. But in that chart, RG213 is really not the best choice to use at VHF and UHF. And they normally use hardline coaxial cable, which instead of having a braid as that outer conductor, it's actually copper tubing that's corrugated, so you can bend it a little bit. And they center the center conductor with some spacers, but some of it uses foam as the dielectric. It has more loss than the air part line. Like I said, most of the repeaters are going to use hard line to go from the transmitter of the repeater up to the antenna. Which of the following types of feed line has the lowest loss at VHF and UHF?
D.
Air insulated hardline. And the larger the diameter, the lower the loss. And the higher the cost. Even connectors for hardline are $25, $50 probably for the smaller stuff. Okay, there's many factors that can cause losses in coaxial cable. The biggest one is water intrusion. Water can get into the dielectric, especially if it's foam, and be absorbed in the foam, so it changes the dielectric properties. It also can get into the braid. If it has copper braid on the outside, which most of the better ones do, they'll have a double shield. Typically, they'll use like aluminum foil and then a copper braid over the top of that. But if the water gets into the jacket, it basically corrodes the copper braid and breaks it down, and it no longer conducts and becomes very brittle. I just saw a video last night from a guy that sells this stuff, and he was talking about the effect of water and all that, showed some examples, and it was amazing how much damage water could do. So, talk about it again. The other thing is running with a high standing wave ratio, because what that means is you're going to heat the cable up more, right? When you transmit power through that coax to the antenna, so you're running at 100 watts, if you had a perfect match, okay, you're going to get that 100 watts to the antenna, and it's not going to reflect any of it back because it's a matching impedance. In most cases, that's not exactly true. It won't be a perfect 50 ohms. So some of that power is going to be reflected back kind of out of phase. So as it gets reflected back through the coax, whatever loss there was in that coax, it's going to see it again. So on the way up, say you had 1 or 2 dB loss. Well, let's make it worst case, 3 dB loss. So you get 50 watts of your 100 watts to the antenna. It's not matched, so it reflects a portion of it back, and you got another 3 dB loss of the reflected signal, which, if there's any left by the time it gets back to the transmitter, may get reflected back up again, okay, and incur loss on the way until it's all absorbed and lost in the coax, which produces heat, okay? Whereas the antenna radiates the signal, any power that's absorbed in the coax is generated as heat. So that heating gets worse the higher your SWR is, and the more lossy your cable. So that will affect the cable. It'll high enough, it'll affect the dielectric, particularly if it's like a foam. And then in addition, if you got a lot of connectors in line, every connector will have a little bit of a mismatch, which may be a little loss, but definitely a little bit of an SWR mismatch, which will add to the reflection loss.
So on external connections, would you recommend using like a heat shrink tubing?
No. You need to use a sealing tape. 3M makes some that they use for. Did I lose you?
No, I'm still here.
Is that like the self-vulcanizing tape?
Yeah. There's a bunch of 3M varieties that they use for commercial stuff where it's not like your cheap, what they sell is electrical tape. It's more rubbery and stretchy, and it basically glues itself to itself. So you wrap it starting below and you spiral it up from the coax totally over the connector all the way up to the mating connector. So you seal it. LMR times microwave sells some for a little more money than the 3M. Supposedly it works a little bit better, but it's the same type of deal.
Yeah.
And theirs is UV protected. Some of the 3M that I've tried, you have to put a second covering of regular tape over it to protect it from UV, because the rubber part of it, you just all wrinkle up. But when you put it on, you need to stretch the tape so it will actually act like shrink wrap after a while.
Yeah,
And the sun gets to it and it shrinks and makes a waterproof seal,
it sounds like the stuff I used to use many years ago on aircraft,
probably.
wiring and connector
Yeah.
sealing, yeah.
Yeah, anything that's made to do that for the commercial stuff, like the power company uses. And there's so many brands of 3M stuff, it's hard to say which one is which. But I know there's at least one of them that's almost like rubber stuff, but it doesn't hold up the UV. You've got to put something on top of that. It seals well, but
Yeah.
you got to protect it.
I think if you did a heat shrink, you'd still get potential for water if the water pressure was high enough.
Now you can get heat shrink that has a heat sensitive adhesive in it, which I've used to make some common mode chokes, ferrite beads over the coax, and you seal it up with shrink and use the adhesive, and it's got a real thick glue that when you shrink it, it oozes out. It really seals. It's watertight. The one advantage to the Times microwave or the 3M stuff is that it's easy to take off. You can
Nice,
just
easy
kind of
slit.
slice it a little bit with a knife and peel it right off. Some of the stuff they sell at the amateur radio places, coax seal, I think it's the name of one of them, several of those. And it just, a lot of it's white. It forms this mushy thing around it. I mean, it seals, but it's really messy and it sticks. I mean, you can't just peel it off.
Just hope you don't
have
have
to
to
scrape it
repair.
off.
Yeah.
Okay, so which of the following is the source of loss in coaxial field line? Feed line, excuse me.
Delta.
D.
Got a lot of
We have
all
this
these
time.
choices here.
Yeah. Half a dozen or more.
Okay, moisture is probably the biggest cause of feed line loss, but ultraviolet light can affect the outer jacket depending on what material it is. And you can get some coax that says it's UV resistant. If it's not, after a period of time, and depending on the exposure, that outer jacket will get cracks in it, will allow water to come in. So again, it turns out it's really water, but it's a result of cracks in the outer jacket. Now, you wouldn't think you'd have that problem with the hard line, but you really got to be careful and make sure that any joints or anything are,
And you're not going to have much,
soldered or welded, so there's no.
you're not going to have much air insulation if it's full of water.
Right. And the hard line does require special techniques and tools to make sure that you don't have any voids or anything where water can get in.
Do they have to evacuate those? I mean, like put a vacuum pump on or
I don't know.
fill them with nitrogen or something?
I would suspect in some cases they do that where it's really serious stuff. I know, like the telephone and a lot of communication stuff when it's underground will be pressurized to keep water intrusion out. So you have all along the line, you have pumps keeping the air pressure up. So any leak, air comes out, water doesn't get in.
Right.
Okay, which of the following causes failure of coaxial cables?
A.
Water. Why should the outer jacket of coaxial cable be resistant to ultraviolet light?
D.
Hey, sure sounds nice.
Harsh radiation. losses in the cable's jacket. Since it's an insulator, I guess it is. What is a disadvantage of air core coaxial cable when compared to foam or dielectric types?
D.
Special techniques and tools. Okay, connectors. There's a lot of connectors you'll run into in the feed line. You're gonna normally have a PL259, which is the male, or an SO239, which are, they call them UHF connectors, but they're really VHF and HF connectors. They don't work that well at UHF. Sometimes in the shack, you may have cables with B and C connectors, which is a bayonet or a quick disconnect. For things that you may want to patch around, connected test equipment. You know, most things like oscilloscopes and signal generators and those kind of things will have B and C connectors on them. If you're really dealing with high frequency stuff, it's an SMA connector, which is about a 1/4 inch threaded connector, and they're good up into the 10, 12 gigahertz range. But because of their size, they work with small diameter coaxes, so you'd only have short runs of those because of the loss. There's a type N, which most people that are serious use for UHF. Some people use them for VHF and HF because they're claimed to be waterproof. I don't exactly know how that works, and I haven't used them much. They cost 2 to 3 times as much as a PL259. But the PL259 is the most common that's used. Chinese companies make a lot of them, so there's all different varieties of PL259. Some are better than others.
Quality control, maybe not as
Most
good.
of the Chinese ones are maybe not the best. The plating and stuff like that will be different. Amphenol makes good ones. Of course, Time Microwave, but they mostly make end connectors. If you buy them off of Amazon, you know, roll the dice.
Mm-hmm.
You might get good ones, you might not. I bought some end connectors from them a few weeks ago. Was looking for a female cable connector in, and I had a hard time finding them, and I found them on Amazon. Price wasn't bad. I got them. They're crimp connectors, no ferrule. They refunded my money, but okay, here's a picture showing a variety of them. They're little SMA connector over here on the left. The end connector, and if you compare it down here to the far right, which is PL259, it's about the same size, but the center conductors are different. How it gets its waterproofness, I'm not sure, but they do claim they're waterproof. There's a TNC, which I'm not familiar with, an SMC, which is similar to an SMA connector. This little MCX, you probably have some and don't know it. If you were to look inside of your cell phone or your laptop, you'll have these connectors connecting the antenna to the circuit board, and they're much smaller than they look in this picture. The BNC connector, the bayonet, which is also out of proportion. It's not nearly as big as N, or it's only, what, maybe 3/8 of an inch, I guess. An SMB, which is like a reverse polarity of an SMA, I think. I don't know about a mini UHF. I've never actually seen one. It's essentially just showing the different frequency ranges for them. So you can see that N connectors and SMA connectors are the most popular that you're going to see up there in the gigahertz range. Which of the following is true of PL259 type connectors?
B.
Say Charlie?
Charlie.
Which of the following RF connector types is most suitable for frequencies above 400 megahertz?
Bravo.
Okay. Yeah, you could use the PL259, but N's are better for that frequency. And you definitely wouldn't use a DV25. That's the old parallel port 25 pin D connector.
They don't even talk about those anymore.
No, they're hard to find. And I don't know what an RS-213 connector is.
So coming off the back of like a base station radio, I mean, the most typical connection is going to be the 259 though, right?
Yeah, that's actually the female part, so it's an SO-239.
Cable would have the 59.
Yeah, the male, which normally you have on the cable, would be 259. However, you can get cables with the SO-239s on one end or both.
Yes.
But most common is you're going to have a 259 male connector on your coax, and your equipment, like your transceiver or your watt meter or tuner, all those things typically will have a SO-239 bulkhead connector on the back.
You could use your feed line as an adapter per se if it had like an N connection on one end and then the 259 on the other, right?
Yeah. Right. If you had an antenna that had an N connector, I mean, you could buy or make your feed line with an N on one end and a 259 on the other. And there's they make adapters that screw on.
That's what I was thinking, like almost like a pipe nipple.
Yeah.
Different.
They make adapters to go from pretty much anything to anything. You can get a PL259 to an SMA or to a BNC or an N in opposite directions and opposite sexes. Okay, so connectors can be difficult to install properly. One of the things you have to be careful of is the shield of trimming those wires so you don't have stray strands sticking out that when you put the connector together can short with the center conductor. And if you don't have good connection with the braid, for instance, or you didn't solder the center conductor, or in some cases, I think they can crimp them. You can get a high SWR because you don't have a good connection. So you got extra resistance in there and maybe even capacitance. If it's just close and not making actual contact, it would act like a capacitor. So you need to make sure that you properly crimp or solder the shield and the center conductor. Make sure that when you make the connections that they're actually screwed on all the way. Sometimes it'll feel like it's there and it's not. So, and they they tend to loosen up some. I think you see that more on the cheaper Chinese versions because the tolerance on the threads, and they don't seem to tighten up as well. So that's something you need to check periodically, is make sure that the outer ring on your connector is tight. Sometimes you'll find you can turn it maybe a quarter of a turn. So that can give you a high or an erratic SWR reading. So you just need to verify that you got good connections from one end to the other at your antenna, at everything in between, and at your transceiver. So what can cause erratic changes in SWR?
B.
I'll pick the loose connection or a cheap SWR.
Yeah.
Which I think I have one at home, is a real cheap one.